All right, one more little video on our exponential functions. And the last type of exponential function we're going to talk about is something called the natural exponential function. Okay, now this is basically just a function that has a special base. Okay, so you'll see here our natural exponential is e to the power of x. Okay, now this e number is our natural base. Think of it as sort of a special number like pi. Okay, so e is approximately 2.718282. Just like pi, it's an irrational number, so it can't be written as a fraction, and the decimals never end and they never repeat. Okay, now this base in particular is useful in a lot of different application problems. So if you're looking at something like population growth, you're looking at different finance examples like compound interest, or maybe you're looking at the growth rate of some sort of epidemic, all right? How these things grow over time tend to be exponential, and the natural exponential in particular is a really good way to model a lot of these application problems. So what I want to do is graph this function, and we'll see that it's very similar to our other exponential functions. And then we're going to look at a few application problems with both this natural exponential as well as just exponentials in general. So let's go ahead and graph f of x equals e to the power of x. Okay. Now the nice thing is if we pull up our graphing calculator, our calculator has an E button right on it. So all we need to do is hit second and then this LN button that's right next to the 4, and that'll pull up your little E where you can type in these numbers. Okay, so let's go ahead and let's make a little table as we've done in the past. It's a really crooked line. There we go. Okay, and I'm just going to go with the same -2, -1, 0, 1, and 2 for my x's. Okay. All right, so if we plug these into our function, and I'm just going to use my calculator to do it. So I'm thinking e to the -2. So again, I'm hitting second, that ln button, and then just enter, of course. And I've already got it pulled up right here. Okay, e to the -2 is approximately 0.135. Okay, and e to the -1, again, I'm hitting second, the ln, putting in my exponent of -1, and then enter. All right, and that is approximately 0.368. Okay, e to the 0, that one I don't have to plug into my calculator because I know anything raised to the power of 0 is 1. E to the power of 1, I'm hitting second, ln, putting in my exponent of 1, and then hitting enter. And that comes out to about 2.718, which is of course just our E number. All right, and then E squared, again, I'm doing second, ln, putting in my exponent of 2, and then enter. And E squared is approximately 7.389. Okay, so they're not pretty numbers, but that's okay. All right, so now we're going to graph this like we've done all of our others. Okay. I count my 2's here to make sure I fit this on here. All right. As I said before, I don't really care what you count by on your scale as long as it's consistent and labeled. Okay, and just do your best with the decimals. So we have -2.135, -1.135, 0.368, 0, 1, 1, 2.718, and then 2, 7.389. All right, so just like we saw with all of our other exponential functions, these are going to be approaching a horizontal asymptote of y equals 0 on the left, and then just increasing to infinity on the right. So it has, again, this horizontal asymptote at y equals 0. It's increasing from left to right, so it's exponential growth. Okay, and the reason why it's growth is because e is a number bigger than 1. Our base is bigger than 1, so it's increasing from left to right. Okay, and then lastly, let's also write out our domain and range. So domain, reading it from left to right, is the same as all of our exponential functions, all real numbers. And then range, reading our graph from bottom to top, goes from our horizontal asymptote at 0 up to positive infinity. Okay, so let's go ahead and let's look at a few application problems. Okay, because we haven't done any applications yet. So our first one, it's not using this natural exponential yet, but we're just kind of looking at exponential functions in general. So it says a common bacterium with an initial population of 1,000 triples every day. And this is modeled by this function here. Okay, so 1,000 times 3 to the power of t. Now that makes sense because if it's an initial population of 1,000, our a value is 1,000, and it's tripling every day, which means our base is 3. All right, so I want to find the population after, let's say first I want to do 12 hours. So I want to know how many bacteria we have after 12 hours. Okay. All right, so it's telling us that t is the number of days. So 12 hours would be half of a day. So I'm going to plug 0.5 in for my t. We have 1,000 times 3 to the power of 0.5. All right, and I'm just going to plug that into my calculator, and it gives me 1,732.05. Now we're talking about bacteria here. It doesn't really make sense to have part of a bacteria. I'm going to go ahead and round that to about 1,732 bacteria. All right, let's also see how many we have after 2 days. Okay, so 2 days, we would be plugging in 2 for our t. Again, just plugging it into our function. So 1,000 times 3 to the power of 2, and that would come out to 9,000 bacteria. Okay, so this is one example of where we can use these exponential functions is in population growth. Okay, this is an example of population growth of bacteria, but it also applies to population growth of people, population growth of animals. Okay, any type of population growth is generally measured by exponential functions. All right, another example of where we can use these exponential functions is in things like inflation. Okay, so this one, we're assuming we have an inflation rate of 5% per year. And we have this model then, P of t is equal to P naught, which is our initial price of an object or an item, times 1.05 raised to the power of t. Okay. Now the reason it's 1.05 is because since it's increasing at 5% per year, the 1 is saying you're taking whatever your starting price is and then you're adding the 5% to it. So it's 100% of what you already have plus the 5% inflation rate. Okay, so if we're given this model, it says that our t is in years on this one. We want to know what will the price of a new car be in the year 2020, so this year, if it costs $16,000 in the year 2014. Okay, all right, so Essentially then, we're thinking from 2014 to 2020, there's a difference of 6 years. Okay, so we're looking for when t is equal to 6. And the cost of that car in the starting year, in 2014, excuse me, is $16,000. So our P naught, our initial price, is $16,000. So we're looking for P of 6. It's going to be 16,000, and then times 1.05 raised to the power of 6. Okay. Plug that into your calculator, and you're going to get 21,441.53. Okay, so assuming a 5% inflation rate, which that does vary, okay, sometimes 5% might be accurate, sometimes 2 might, sometimes 7 might, okay, it just kind of depends, but assuming a constant inflation rate of 5%, this is how much you could expect that car to cost in 2020. All right, let's go ahead and look at one more application problem. And this one's going to be using that natural exponential function that we looked at the beginning of this video. All right, so this one says in 1969, the world population was approximately 3.6 billion with a growth rate of 1.7% per year. Then we have this function that is describing that world population. F of x is in billions, and x is years after 1969. So let's again use this function to estimate our world population. Let's do a couple different years. Let's say, first of all, we just want to do 1969. Okay. All right. Well, if x is years after 1969, and we're looking at the year 1969, then we're just going to be plugging in an x value of 0. So we would have 3.6 times e to the power of 0.017 times 0. And if we plug that into our calculator, we would get 3.6. And remember, this is measured in billions. So 3.6 billion people in the year 1969. Now, of course, that's good that that tells us that, because that's what it's supposed to be. That's what we were told to begin with. All right, let's do one more year. Let's say we want to know in the year 2000. Okay, so step one is to figure out what our x value is. Okay, so x is years after 1969. So if we take 2000 minus 1969, that's a difference of 31 years. So f of 31, we have 3.6 times e raised to the power of 0.017 times 31. And if we plug that into our calculator, we get about 6.1 billion people. Okay, so again, this is an example of how these exponential functions can be used. Okay, estimating and measuring the growth rate of different populations. All right, guys, so that is the end of our exponential functions for now. So work on your homework, work on your labs, and as always, email me if you have any questions on anything.